Calculus. For so many of us, it's the final boss of high school math, right? It's this gateway to amazing careers in science and tech, but it's also a wall where a lot of ambitions just come to a stop. Today, we're going to unpack why. Okay, so get this. A study in the Journal of Research in Science, Mathematics, and Technology Education found that in some universities, up to half of all first-year students fail their calculus classes. That is a huge number. It's a signal that something is going fundamentally wrong for a whole lot of people. So, what is it about calculus that's so tricky? In this explainer, we're going to zero in on one of its toughest challenges, these things called optimization problems. We're going to investigate why finding the best or most efficient answer is such a massive hurdle for so many. To really figure this out, we've got to see how students are actually thinking when they're in the middle of a problem. So we're going to use a South African research paper as our case file here, looking directly at the work of high school students to diagnose, where does the confusion actually start? So check this out. This is an actual student's worksheet. They were trying to solve a pretty classic optimization problem. They had an equation for the volume of water in a tank, and they were asked a very specific question. How fast was the volume changing at exactly week 5? Not how much water was in there, but how fast it was changing. And here's where it gets really interesting. This is the students' own reasoning. They figured out the total volume at week 5 and then just divided it by 5 to get an average. Now, this isn't just a simple math mistake. This reveals a huge and actually very common misunderstanding of the whole idea. This is what researchers call a conceptual error. The student mixed up the total amount of water with how fast the water level was changing in that instant. Think of it like this. When you're driving a car, the odometer tells you the total distance you've traveled. That's the function's value. But the speedometer? That tells you how fast you're going right now. That's the derivative, the rate of change. This student was basically looking at their total mileage to figure out their current speed. It just doesn't work. Okay, now let's look at another student, L8. This case is fascinating because this student actually got part of the problem right. They used the calculus steps perfectly to find that the maximum volume happened at 1 week. On the surface, it looks like they've totally got it. But then, the researcher asked them to explain what their answer meant, and the whole thing just crumbled. When they were asked what a negative sign in the rate of change meant, the student said it meant going left. That's a concept from physics that has absolutely nothing to do with the volume of water in a tank. So here's the kicker. This isn't just a mistake, it's a language error. The student was fluent in the procedure, but they didn't speak the actual language of calculus. A negative rate here just means the volume is going down, it's decreasing. This shows so clearly that just memorizing steps isn't the same as understanding what any of it really means. So the researchers boiled these struggles down into 4 main types. We saw conceptual errors, like mixing up the total amount with the rate of change. Then there are generalization errors, where you apply a rule where it doesn't fit. We just saw a big language error, where the words and symbols are misunderstood. And finally, hidden errors, which are just little procedural mistakes that are buried in the math. Knowing what these are is the first step to fixing them. Okay, so we've diagnosed the problems. Now, what does the right way look like? For that, we're going to turn to an expert source, the Fiveable Study Guide for Calculus 1. It lays out a super clear playbook for how to nail these problems. According to Fiveable, the entire game is pretty much won or lost before you even start doing any calculus. It is all about the setup. First, you have to clearly identify your objective. What is it you're actually trying to make bigger or smaller? Second, what are your constraints? What are the rules holding you back? And third, translate all those words into nice, clean equations. A really good tip? Just draw a picture. Label everything. It turns a confusing paragraph into a clear map. And let's be super clear on this, because this is a huge trap for people. The objective is where you want to go. The constraint is how much gas you have in the tank. You want to maximize the area of your garden. That's the objective. But you only have 100 feet of fence. That's your constraint. You just can't plan the trip if you don't know how much fuel you've got. And right here, this is the expert definition that just completely corrects that first mistake we saw. A derivative is not an average over time, it's the measure of the instantaneous rate of change. It's the speedometer, not the trip odometer. It's all about what's happening right now. And finally, once you think you've found the peak of the mountain, how do you prove it's actually the top? Well, experts use 2 main tools. The first derivative test basically checks if you are going uphill and then started going downhill. The second derivative test checks if the curve at that point is shaped like a frown or a cap over the peak. This isn't just about following steps. It's about having the mindset of a real problem solver. You always, always double-check your work. Okay, so we've got the student's struggles on one hand and the expert's playbook on the other. So what happens when we put them side by side? Well, we uncover the massive difference between just doing math and actually understanding it. This quote from the research paper just hits the nail on the head. The students weren't failing because they couldn't follow a list of steps. They were failing because they had what's called an instrumental understanding, but they were missing the conceptual understanding. Think about it like this. Instrumental understanding is like knowing a recipe. You can follow the steps, you mix the flour, the sugar, the eggs, and you'll probably get a cake. But relational understanding, that's knowing the chemistry. That's understanding why baking soda makes the cake rise and what would happen if you use too much. The student struggle lives right in that gap. The way you get across is by constantly asking why. Why does this formula work? What does this symbol actually mean here? That's the bridge. And this right here tells the whole story. Let's go back to learner L8. On the left, we see perfect execution. They knew the recipe cold. But on the right, when they tried to explain it with that going left idea, it shows they had no idea about the chemistry of what they were doing. So, there it is. This one student's worksheet shows us everything. It's the perfect snapshot of that gap between knowing the steps and truly getting the concept. Knowing the recipe got them an answer, but not understanding the chemistry made it impossible to solve the whole problem. So you might be thinking, okay, that's kind of interesting for a math class, but why should I care? Well, because it turns out this way of thinking, this whole art of optimization, is one of the most powerful tools we have for dealing with the real world. Optimization isn't just some chapter in a textbook. It's everywhere. Every time a business figures out the absolute cheapest way to ship its products, or an engineer designs a bridge using the least possible amount of steel, that's calculus. Every time a doctor figures out the best dose for medicine to get the maximum effect with the minimum side effects, yep, that's calculus at work. And that brings us to the most important takeaway from our expert source, and really the core of this whole thing. The goal is not just to memorize the steps. It's to build that bridge to understanding the why behind them. That's the difference between being a human calculator and becoming a real-deal problem solver. Which kind of leaves us with one last thought. Is the point of learning all this math just to find the right answer? Or is it to learn a new way of thinking, a way to ask smarter questions about the world around us, and then figure out the best possible path forward? I think the Calculus Conundrum shows us it's definitely the latter.